Okay, we're going to talk about 2,7 and 2,8. So first I'm going to write down an example. Given big G of t equals 1 minus 2t over 3 plus t, find G prime of 1. So before we dive into this, there's actually 3 ways to do this problem. So I just want to talk about that a little bit. This is a 2.7 problem, but now that we've covered 2.8, that gives us another way to do it. So there's 2 definitions in 2.7. Definition 1, you could do it that way. You could use the other definition, so with h in it. Or you could use the 2.8 definition, then sub in t equals 1. Now you can do any of these 3 ways. It's totally fine. The way that I'm going to choose to do it is with 2.7 definition 2, which is h goes to 0. Some people like the other definition that has x goes to a, and that's totally fine. I've just found that if I give like some blanket advice, the one with h in it works better for most people. All right, so there are 3 ways to do this, and any of those are fine. Now I don't suggest you do the 2.8 one because this is going to be harder than it has to be. So I should mention that just doing the 2.8 definition all the time and then back subbing, that's a harder way to do it, and it's longer. So probably not the best way for this particular problem. So definition 2, you don't need to know that by name. That's the one with h in it. So the limit as h goes to 0 of big G of h plus a, which in this case is what? 1. So we're finding the derivative at 1, which is the slope of the tangent line at x equals 1. So we start out this way, and now we're going to have to use our limit notation throughout. Don't forget, you'll get points off in the test if you don't do that. And now we need to plug in h plus 1 into that big G function. So notice that, well, first of all, it's in terms of t. So we're not replacing x, we're replacing t because that's the variable for that function. And there's 2 of them, so we have to be careful that we're getting that h plus 1 in both places. So it's 1 minus 2 parentheses h plus 1 all over 3 plus, instead of t, parentheses h plus 1. So that's a really critical step. If you don't plug in the h plus 1 right, the rest is going to fall apart, and you're not going to get much credit. So that's the g of h plus 1. Minus g of 1, you could just do side work. That's just substituting 1 into the function. Or you can just do it in the context of this larger problem. So 1 minus 2 times 1 over 3 plus 1. Now all of this is over h. All right, now let's find the answer to the 1 minus 2 times 1 over 3 plus 1. That's just going to be a value. And then also let's just go ahead and simplify things a little bit in the first fraction. So we have this equals the limit as h goes to 0 of 1, and then I need to distribute like a minus 2. So minus 2h minus 2 all over 3 plus h plus 1, where the parentheses aren't actually doing anything, so I get h plus 4. Okay, what else do we have? Well, we find 1 minus 2 and we get negative 1, and then we have, oops, doing too much at once here, minus, we'll just do this, negative 1 over 4. So that'll be plus 1/4. Still have some simplifying to do in that first fraction. 1 minus 2h minus 2. Let's write this as negative 1 minus 2h over h plus 4 plus 1/4. Okay, so not totally simplified here, but at least clean things up a little bit locally with those two fractions. So now, you don't even have to bother trying to plug in h equals 0. You're going to get 0 over 0, which is indeterminate form every time. So the algebra for this, when you're given a function that's a rational function, in other words, it's a fraction, then the algebra here is to just simplify that thing. So we have a compound fraction here where we got fractions within a larger fraction for our limit as h goes to 0 thing. And so there's two main ways people simplify this. Either they get like terms on the top and combine them and then take care of the division by h, or we learn this little trick, which is a little more efficient always, as it turns out, for this problem. So I'll just do it that way, where whatever that common denominator would be for the top, multiply both the overall numerator by that and the denominator. The next step can get a little tricky for people because they kind of over distribute or something like that. This 4 times h plus 4 is like it's over 1, and so we multiply through using distributive property on top. It only goes to the top of those fractions. So we have negative 1 minus 2h in parentheses times 4 times parentheses h plus 4 all over h plus 4 just by itself down low. The 4 times the 4 plus h does not also go to the bottom of that fraction, just the top. So we'll cancel some stuff in a minute, but then we have the 1/4. So on top it's 4 times the quantity h plus 4 all over 4. And that's all over h times 4 times h plus 4. So I'll take a little break there. That's a critical step. Any questions? So let's do the fun part and cancel. The h plus 4s cancel out of the first one, the 4s of the second one. So what this little step did was clear all the fractions in the problem. Then on top we're going to want to simplify, so I'm going to distribute the 4 that's left behind for that first fraction that we had. And so we're going to get minus 4 minus 8h plus h plus 4 on top. Now in the bottom, should I multiply through the 4h? No. What is the problem child for this? Always h. H over h is what's creating the 0 over 0. Because when you plug in h equals 0, you know, that's what's creating that. We just can't see that on top yet. We're getting there. But in the denominator, we know that h is the problem. That's what, when you plug in the 0, 0 times anything is 0. So that h right here is the one that's creating that problem, and we want to keep it factored out so we can cancel it with the h on the top eventually. Okay, good. So limit as h goes to 0. Simplify the top. So we get negative 8h plus h is what? Negative 7h. And then, ooh, those other terms go away. Which is pretty critical, actually. Otherwise, we won't have a factor of h on top. So if you don't get a factor of h on the top and h on the bottom, you know you messed up, and you should go back and figure out where you went wrong. If you run out of time on the test and that happens, then like just write that down and maybe move on if you're not finding it, and then come back to it when you're done with everything else. So now we can just go ahead and plug in h equals 0. So we have negative 7 left on the top, and then a 4, plug in h equals 0 for that h, lone h that remains, and we get a result here, negative 7/16. Questions?
When is it okay to drop the limit notation?
The correct time to drop the limit notation is when you're plugging h equals 0. So just as I showed it there, is when you should drop it. And we won't be too harsh if you write the limit notation in the beginning and then you write it like in the last step that's appropriate. Now it should be said, don't put limit as h goes to 0 in front of this other business after you plug in h equals 0. You know that you drop it on purpose there, and it's correct to do so. Other questions about this one? Yep. It's up to you. So I like this one. This is the one I try to push onto people. But if you want to use x goes to a1, that's fine. The x goes to a1 has a factor of x minus, like x minus a in the bottom, and then you have to factor the top to that, and some people just are awful at factoring. Whereas factoring out a common factor of h is way easier for people, but the flip side is the algebra that I did to get there is a little bit harder. So, I mean, it's kind of depends on your skill set on which one you want to do. So whatever one's fine. Other questions? Okay, let me stop the recording.